All right, well, in this screencast, we're going to now go over these elevator problems as well as these incline plane problems. So we'll start with these elevator problems, and we'll start with the first one, part A, where we've got an elevator which is moving up at constant velocity of 5 meters per second, and the mass of the person is 70 kilograms. And we have to answer these questions. We have to find the weight force, the net force, the normal force, and the number of G's. So let's go ahead and do that for part A. All right, so we'll draw in a little elevator. And we will draw in a person. Now, in this elevator, we've got a couple of forces acting. We'll have the weight force acting downwards, and we know that the weight force is equal to m times g, which is going to be the mass of the person, which is 70 kilograms, multiplied by, I'll approximate g to 10, so multiply that by 10, and so that will equal 700 newtons. Actually, before we proceed, we want to designate our positive and negative directions. Because this person's moving in the upward direction, the whole elevator is moving up with a velocity of 5 meters per second, actually. We'll designate up as positive, and therefore we'll designate down as negative. So in actual fact, the value of the weight force is negative 700 newtons. Okay, now we also know that there's going to be a normal force. Now we don't really know the size of the normal force yet, we'll just draw it in like that. Now remember, the normal force is actually the force that the elevator is pushing up on the person at, so it's actually being applied through the floor of the elevator at the point of contact with the person, through their feet basically. So let's look at our questions. We have to firstly find the weight force, so we've found that it's 700 newtons acting down. The net force, well, let's have a look at the net force. We know that the elevator is moving at 5 meters per second at constant velocity. Now this is a really key point here. Constant velocity. Now we should now know what this implies. This has big implications because we know that constant velocity means that acceleration is equal to 0, which implies that the net force is equal to 0. So what that means to us is that all the forces that are acting, and in this case there is 2, both these forces will add up to produce a net force of 0. So let's see what we can do now. Remember, the next step was to actually connect the two forces with the net force. And remember, the net force is by definition all the forces that are actually acting added together. And so as a vector, the net force is going to equal the normal plus the weight force. So if we have a look at our directions, the normal is going to be a positive and the weight is going to have a negative value. So that means that if we substitute our values in now, the net force, which is 0, so 0 equals the normal force, which is what we're trying to find, plus the weight force, so that's going to be negative 700. So the weight force is negative 700. And therefore, if I move the negative 700 to the other side of the equation, the normal equals 700 newtons. So we've now found a net force was 0 and the normal force is 700. The final thing was to work out the number of G's. Well, the number of G's is equal to the normal force divided by the weight force, or it's that ratio, the absolute value of that ratio, and in that case it's going to be 700, which is the normal force, divided by 700, which is 1. So they're experiencing 1 G. which is what you would be experiencing if you're just sitting in a chair doing nothing. Okay, so that's the first question. Okay, I'll clear this and let's look at the second question. Part B. All right, in part B, the elevator is accelerating. It's the same person. They're accelerating downwards at a rate of 1.5 meters per second squared. Okay, so elevator and our person. And they're accelerating downwards. There is an acceleration and it's downwards and it's 1.5 meters per second squared. Okay, so the weight force for this person will be the same as in the previous problem. So the weight force will be acting down and it equals 700 newtons. And we'll keep the same direction as we did before. So we'll say that up is still positive and down is negative. And there will be a normal force, which is acting in the upward direction. Now, once again, we now need to link our normal force with our weight force with the net force. Now, if we look now, there is an acceleration, so there is going to be a net force. So once again, we know that the net force as a vector is going to be the addition of all the forces that are actually acting on the person, which is the normal plus the weight force. And they are vectors, of course. Okay, now we know the weight force is going to be negative 700. We're trying to find the normal force, but we also need to find the net force. So to find the net force first, we can use Newton's second law, of course. So the net force is equal to ma, that's Newton's second law, which is the mass of the person, which is 70, multiplied by the acceleration, which is 1.5, and that's going to be half of 70 is 35, so it's going to be 105 newtons. Now, because the acceleration is acting down, the net force is always acts in the same direction as the acceleration, so the net force is acting down and the acceleration. So that will be a negative value because it's acting in the downward direction. So let us now see if we can work out the normal force. So the net force, which is negative 105 newtons, so it's going to be negative 105, is going to equal the normal force, which is what we don't know, plus the weight force. Well, the weight force is negative 700 because it's acting down also. So there we go. So therefore, if I move this value to the other side of the equation by adding it to both sides, then I end up with the normal force is equal to, that will be 595 newtons. Okay, and that means, well, we know what the net force is, we know what the normal force is, and it's a positive value because it's acting up. We can now work out the number of G's. The number of G's is equal to the ratio of the normal force over the weight force, and that will equal 595 over 700. 595 divided by 700 is 0.85. So that equals approximately 0.85 Gs. Okay, that's the second problem done. The third problem, the person is accelerating upwards at 45 meters per second. Wow, that's a pretty enormous acceleration. So let's check this one out. So we've got our elevator and the person is standing in the elevator once again, and their mass is the same as the previous problems, and therefore their weight will be the same. So their weight will be mg, which is going to be 700 newtons. And for the sake of consistency, I will maintain that up is positive and down is negative. Remember, it doesn't matter at all which way you call positive and negative. It's just that once you've set that up, that anything pointing the upward direction must be positive, and any vector, whether it be force or velocity or whatever, pointing downwards in this problem would be a negative value. Okay, so there's going to be a normal force as well, and let's draw that in. So our normal force is going to be acting in that direction. We know that the acceleration is upwards, and it's a pretty enormous acceleration. The acceleration is 45 meters per second squared. Let's just check that again. 45 meters per second squared in the upward direction. So there's definitely going to be a net force here because there's an acceleration. So let's work out what that net force is. The net force, using Newton's second law, will be ma, which will equal 70 multiplied by 45, which equals 3,150 newtons. Okay, so now we need to work out the value of the normal force. Well, once again, the net force is actually equal to all the forces that are acting added together. So that's going to be the normal force plus the weight force. And the normal force is going to be 3150. Okay, the net force, sorry, I beg your pardon, the net force will be 3150. And the net force will act in the same direction as the acceleration. So it'll be up, which means it's going to be positive. So our net force will be 3150, and that will equal the normal force, which is what we're trying to find, plus the weight force. Well, the weight force is acting down once again, and therefore once again it will be negative, so it'll be minus 700 newtons. So therefore, by moving our minus 700 to the other side of the equation, then that means that our normal force will be 3150 plus 700, and that will equal 3,850 newtons. So that's the value of the normal force. To work out the number of G's this corresponds to, that will equal the ratio of the normal force divided by the weight, the absolute value of that, which will equal 3850 over 700, which equals 5.5 Gs. That's space shuttle acceleration territory there. So, or hardcore fighter pilot maneuvers, acrobatics. So it's a pretty substantial G rating there. Okay, so that was the third one. Let's have a look at the final one. The final problem, the elevator is in freefall. Okay, let's check that one out. So here's our elevator once again. Oh, it's a green one this time. Beautiful. And we've got our person who's standing in the elevator. Now, Freefall is interesting because with Freefall, everything is going to, of course, everything's going to be accelerating downwards at the rate of 10 meters per second squared. But because everything is in Freefall, the person will not feel the push of the elevator fall back up onto them. As a matter of fact, if you're falling down in an elevator, if the cord connecting the elevator was suddenly cut and everything was just falling down to the bottom of the Eureka Tower, as this elevator here's our Eureka Tower, and here's our little elevator. As it fell and plummeted to the ground, for that entire time, the person inside the elevator would feel like they are just floating around inside the elevator. For those few seconds it would take the elevator to hit the ground, this person would feel like they are simply falling through the air, and they can't actually feel the floor of the elevator at all. That's what Freefall is all about. And so because there's no force of contact between the floor of the elevator and the person, therefore the normal force will be zero. So one of the key features of Freefall, if you are in Freefall, the big deal about Freefall is that the normal force will be zero. Okay? So we'll get rid of that. Okay, so we know what the normal force is, and the net force. Well, let's have a look what the net force is. Remember, F net. If they're in free fall, of course, their If they're in free fall, then their acceleration is going to equal 9.8, or we'll approximate it to 10 meters per second squared. Acting in the downward direction, up is positive, down is negative, like the other three problems we've done. So the net force is going to equal MA, Newton's second law. It's going to be 70 multiplied by 10, which is 700 newtons. Okay? So there's our net force. Now remember, the net force is equal to the normal force plus the weight force. Now, the elevator is moving downwards, the acceleration is downwards, and therefore the net force is downwards, which is negative. So our net force, which we've just worked out, will be negative 700 newtons. The weight, well, the weight is just the same as the other three problems. It is 700 newtons in the downward direction, which is also negative. So the weight force is going to be negative 700 newtons. Well, guess what? Negative 700 equals negative 700, and the only way that will occur is if the normal is zero. So, in other words, if I add 700 to both sides, the normal will equal negative 700 plus 700, which equals zero. So we've just confirmed that the normal force is zero. So we suspected that was the case, now we've proven it. And finally, the G's, the number of G's, well, that will be the normal force over mg, and the normal force, of course, is zero over the weight. Well, zero over anything is zero, so they are experiencing zero G's. A zero G environment, zero G means weightlessness. It doesn't mean zero gravity. This person is still experiencing gravity. If it wasn't for gravity, they wouldn't be falling to the earth. So there's definitely still gravity acting on the elevator, and gravity is still acting on the person. It's just that as they are in free fall, they don't feel any normal force, and what they experience inside the elevator as they are falling is a freefall sensation, or like they are floating, which is 0 Gs, but they're certainly accelerating rapidly towards the Earth, and it probably come to a nasty end once they make impact. So that's the fourth elevator problem. Okay, let's now have a look at the ramp problems. So we have to work out the weight, the net force, the component of the weight acting parallel to the slope, the component of the weight acting perpendicular to the slope, and the value of the normal force acting on the person. In this first one, the mass is 90 kilograms and the person's rolling down the hill and the angle is 15 degrees. So let's draw that situation. So we'll use a ruler this time, I think. So there's our ramp, and we know that it's 15 degrees in there. I'm not going to draw the elaborate little skateboard thing. I'm just going to draw a block. Okay. So let's now mark in our forces. Well, this person, what they're doing, if we have another look, they're simply rolling down the hill and accelerating down the hill. There's no motor, there's no rope holding them back up, there's no friction acting here, so they're just rolling down the slope, and there are the two forces acting. The normal, which is at right angles to the ramp, and the weight force, which is straight down. So let's put those in. Okay, so the normal is acting in that direction, and the weight force will be acting straight down. That's the weight force, and that's the normal force. The acceleration is in that direction, down the ramp, which means the net force must also be down the ramp, which means the only forces that are contributing to the acceleration down the ramp are in this direction. Any forces at right angles to the ramp must cancel out. So what we now need to do then, as the problem asks, we want to work out the components of our weight force. So we look at the component that is parallel, at right angles to the ramp, which is that component there. We also need to work out the component which is parallel to the ramp, which is that component there. Okay. So a weight force we can break into two components, one that is at right angles to the ramp acting down in this direction, and the one that is at parallel to the ramp acting down the ramp in that direction. Now I'm going to designate these just so that we can refer to them more easily. I'm going to refer to this one here acting down the ramp as Wx. I'm going to call this component here Wy, just so that it makes it easy for me to communicate to you which force I'm talking about. One little other thing we need to know, of course, is that whatever the angle is in here is going to be the same as the angle in there, so that's also 15 degrees, and our right angle is there. Okay? Now, using basic trigonometry, if that's our angle, and this green line is this green vector is the hypotenuse, which it is, then this is going to be the opposite side, and this is going to be the adjacent side of this hypotenuse. So this is going to be, to work out this side, it's going to be, we're trying to find the opposite, and this side we're trying to find the adjacent. So if you remember, if you're using the opposite and the hypotenuse, it's going to be sine. And if you're trying to find the adjacent and you've got the hypotenuse, it'll be cos. So it'll be car. So we're going to work out this one first. We're going to use sine. So Wx will equal the hypotenuse times the sine of 15 degrees, and the hypotenuse is the weight force. And I suppose we've got to work that out, haven't we? So mg is going to equal, what was that? I think it was 90 kilograms. So just check that. Yes, 90. So it's going to be 90 multiplied by 10. I'll go with 10 just to make things easier. So that's 900 newtons. So therefore, that will be 900 multiplied by the sine of 15 degrees, and the sine of 15 degrees is 0.2588, so that will equal 900 multiplied by 0.2588, and that equals 232.9 newtons. So that's Wx. Wy is going to equal h times the cos of 15 degrees, which will equal 900 times the cos of 15, and the cos of 15 is 0.9659 0.9659, and that will equal 869.3. Okay, so we've now worked out our value for Wx, our value for Wy. And if we now look back at the problem, let's check out what we need to do. The weight of the person on the skateboard, we've worked that out, and we found that to be 900 newtons. The direction and value of the net force acting on the person. Okay. Now, we know the net force must act in the same direction as the acceleration. So the net force must be acting down the ramp. So what we've done, let's have a look at what we've done. We've got our normal force here, and we took our weight force and we broke our weight force into this component and this component. So we can now basically forget about that weight force because we're replacing that with this force and this force. Now, this and this force must cancel, leaving behind this force. So it's this Wx force is the force that is going to accelerate the person down the ramp. So Wx is the net force, so which is 232.9 degrees, 9 newtons. So F net equals 232.9. Now, if we have to work out the acceleration, we now use Newton's second law, where the acceleration is equal to the net force divided by the mass. So it's Newton's second law rearranged. So it's 232.9 divided by 90. Which is 2.59. 2.59 meters per second squared. And that is the acceleration down the ramp of the person. So let's just go over the questions, make sure we've answered them all. The weight of the person, we've answered. The direction and value of the net force, we've just worked that out. It was 232.9 newtons down the ramp. The component of the weight force acting parallel to the slope, well, we worked that out, and that's this value for Wx, which was that, 232.9. The component of the weight acting perpendicular to the slope, well, that's this one, Wy, and we worked that out to be 869.3. And finally, the value of the normal force acting on the person, well, the normal force must be the same as Wy, so the normal force would also be 869.3 newtons. Okay, so there we have the first problem. So I'll clear that. And so look at the second problem. Okay, the second problem, it's very similar. Same mass of person. I have to work out the net force, the weight, both components of the weight, the value of the normal force, and the tension in the cable. There's a cable here that's holding this person. So this person's not moving. They are at rest. They're wanting to roll down the hill, but they're tied to this post by a rope, so they can't go anywhere. So they're just sitting there. So, and the angle is the same as before as well. So let's work this one out. I might actually add a new layer there. There we go. So there's our ramp. And here's our little mass. Oops, no, make it about here, I think. And there's a post or a wall or something here. And there is a rope connecting those two. Now we'll draw in our other forces. The standard forces we know are weight and the normal. So the weight is going to be acting down. So there it is there. And normal acts at right angles to the surface or the plane. Normal is acting off in that direction. So there's our normal. There's our weight mg. Now there's a third force here, isn't there? The third force is the tension. This rope is trying to put, if you think about it, this rope is pulling on this person in this direction. So we can draw that in as well as a force. So as a matter of fact, yeah, this force here, there's going to be a force there, which we'll call T for tension, and that's pulling up this way. But remember, of course, all these forces must add up to zero because the object is not accelerating, it's not even moving, in fact. So we know that velocity is zero, and if the velocity is zero and staying at zero, then of course acceleration is zero, and therefore the net force is zero. So all those three things are happening here. Now, so the weight force here is going to be the same as in the previous problem. So it's going to be 90 times 10, which is 900 newtons. And our components will be the same. Unfortunately, I've forgotten them and I've erased them, so I'm going to have to recalculate them. Although you can obviously, if you've written down the notes, you can just refer to those. But I'll just do this again. It's that component and that component. So, and and this is WY, what I call WY, and that's I'm calling WX. And let's quickly work them out again. WX was 900 times the sine of 15 degrees. Which is 232.9. And WY was 900 times the cos of 15 degrees. They are the same angle, I'm thinking. Yep. So 15 times 100, and that's 869.3. Okay. So now we know the net force is 0, and so now what we can do, because we've now we've replaced our weight force with two components, I can get rid of this weight force, and that's what I'm going to do. So it's like the weight force has been replaced now with these components. And to make things even easier, I'll just rub that out as well. Remember, vectors, you can move them around anywhere you like in a problem. You can move it anywhere you like, provided you don't change its length or direction. So, as a matter of fact, I could simply grab that vector and move it to there, like that. Now, what does that tell me? If it tells me, you can see now, that if the net force has to be 0, which it does, that means that that force must be cancelled by that force, and this force must be the same as this force. So this is telling us that value for t must have the same value, obviously opposite in direction, but the same value as Wx. So the tension force will equal 232.9 newtons in the upward direction. And so this tension force and this Wx component, which is the component of the weight acting down the ramp, will cancel each other out. These two components cancel each other out. The net force is 0, therefore the acceleration is 0. So that's the situation in that problem. Once again, just a few other things. We know that once again the normal will equal Wy, so the normal will equal 869.3, and as we said earlier, the weight force is 900. Okay, in the final problem, we've got a friction of 100 newtons, and the person's now got a motorised skateboard, and they're accelerating upwards at 1.5 metres per second squared. Okay, I have to work out what's the thrust of the engine. Okay, so let's draw that. Now, okay, we'll there's our ramp. And there's our so-called skateboard, just a little block. Let's draw in our forces. Well, we know, let's draw in the ones we know. Firstly, there's a normal force. So, I want a different colour there. normal force. There's our weight force. Now friction force is acting in the direction of the ramp, acting down the ramp. So I'll draw that in like this. There's our friction force. And there's a thrust force. And the thrust force is accelerating this whole motorized skateboard up the ramp in this direction. So the net force must also be in that direction. And so I'll draw it there like that. So these are our four forces, and there's our middle of our object. So we've got here's our thrust, here's our normal force, here's our weight force, and this is our friction force. We know that the acceleration is 1.5 meters per second squared up the ramp. So acceleration equals 1.5 meters per second squared in that direction. Okay, so because we know the acceleration and we know the mass of the skateboard, which I believe is still 90 kilograms, let's just check. Yep. We can now work out the net force. And remember, the net force must be in the same direction as the acceleration. So I'll just draw that in just to make that point. So net force is in that direction there. So we know that the net force will equal MA, which will equal 90 multiplied by the acceleration, which is 1.5. So a half of 90 is 45, so it's going to be 135 newtons. So the net force is upwards at 135 newtons. So let's see now if we can work out the thrust force. Now we know the value of our friction force is 100. We can work out our components. So I'll go with white, I think. So there's the component acting parallel. There's the component acting perpendicular. This is the parallel component here. And those two components, this one, if from memory, was 869.3, just like in the previous problem, 869.3 newtons. This one, and that's WY, remember, and WX was 232, I think, but I'll just double check that. It's 900 multiplied by the sine of 15, 232.9, yep. So it was 232.9 newtons. Okay, so what I'm going to do is what I did before, because now I've replaced my weight. The weight was the awkward one because it's the odd one out when you think about it. All of these are at right angles to each other and therefore really easy to work with. This one, even though it's actually perfectly vertical, it's the only one that's not either parallel or at right angles to the ramp. So that's why we break that into components. But so now what I can do, I can erase that one. I can erase that weight because I'll try doing this, I think. We can erase the weight because we've found its components. So we can just pretend it's not there anymore because we've found these two components which together act as the weight force. And I will move this component here. Try that again. I'll move that component to there, all right? So let's have a look what we've got. Well, this force and this force cancel. So because the net force must be up the ramp, there's no component acting this direction or this direction, so any forces in this plane or this dimension, this direction, must cancel. So that cancels with this value here. So it just leaves us with the thrust, the friction, and this is Wx, okay, the weight acting parallel to the ramp. Now, to make things a little bit easier to follow, I'll just get rid of this force, because that's being cancelled by this force. And so these are the only three forces that are having any effect on the motion of the skateboard up the ramp. So now we're going to use the idea that the net force is equal to all the other forces added together. So the net force is going to equal the thrust force, which I'll just call T. So it's going to be T plus friction, which I'll call F, and then plus Wx. Okay? So the net force is just the other three, all the forces that are actually acting on the skateboard added together. The normal and Wy are cancelled out because that's what they did, so we don't need to worry about them. But before we can continue, because our motion's in now this direction and I've got multiple forces, I'm going to assign a direction. And because the skateboard is accelerating in the upward direction, I'm going to call upward positive, or that way positive, and down the ramp is negative. So that means our net force is acting up the ramp, it will be positive. Our thrust force, well, our thrust force must be acting up the ramp because it's the only thing that could be actually moving the skateboard in the upward direction, so it's also going to be a positive force. The friction and Wx are both going to be negative forces. Okay? So let's put all that information in, and we know the net force is 135. So we know that 135 is equal to T, the thrust force, which is what we're trying to find, plus the friction force. Remember, F was the friction force, and that was 100 newtons, but it's down the ramp, so it's negative, so it's minus 100. And Wx is minus 232.9. So I now need to move that to the other side of the equation by adding it, and I need to move this to the other side of the equation by adding it. So therefore, T is going to equal, so T equals 135 plus 100 plus 232.9. So that's going to equal 135 plus 332.9, which is going to equal 467.9 newtons. And that is the value of our thrust force that is trying to propel the skateboard up the ramp. But of course, because it's fighting friction and it's fighting Wx, even though the thrust is 467.9, it only amounts to a net force of 135 because of the effect of these other two forces. And that is the final problem. So thanks very much. I hope you've enjoyed watching this, and I hope it's helped. Thank you.